and hello. Today's lesson is on factoring polynomials. In a previous lesson, we factored quadratic expressions. A lot of those skills are going to show up again, but I'd like to extend what we've done to any polynomial, whether the degree is 2, 3, or even higher. So we'll learn a few different strategies, but I'd like to revisit our volume model for multiplication. Here we have the exact same rectangular prism from the previous lesson. The red region has a volume of x cubed, the blue region has a volume of 4x squared, the green region has a volume of 2x squared, and the yellow region has a volume of 8x. What I'd like to do is I'd like to try to reason out what the dimensions of each piece are. So since the red piece is a cube, and its volume is x cubed, that can tell us that the side lengths are all x, x, and x. So now I'd like to find the dimensions of the green piece of the entire rectangular prism as well. But I'd like to note that it shares two sides with the red piece. It shares the depth and it shares the height. So I can copy those two pieces over, and that's an x by x. And now that we know the depth and the height and the volume, we can reason out what the width is. So the length of the third edge of the green prism has to be 2, because that gives it a total volume of 2x squared. So ultimately what we've shown is that the width of the red piece of the cube is x, the width of the green piece is 2, so the width of the whole thing, of the whole rectangular prism, is x plus 2. So we can use a similar relationship from the green piece to find the dimensions of the yellow piece. So the yellow piece shares its width with the green piece, so the width has to be 2. It shares a height with the green piece, so the height has to be x. The only thing it doesn't share is its depth. But since we know the volume is 8x, we can find the depth and reason out that the depth has to be 4. So that tells us that the depth of the whole rectangular prism is x plus 4. And then we know the height is x. So we know the dimensions of this prism are x, x plus 2, and x plus 4. By multiplying this out, we'd end up back at the same place we did yesterday, with the total volume being the sum, which is x cubed plus 6x squared plus 8x. All right, that is our total volume, which factors into x, x plus 2, and x plus 4. But I'd like us to be able to factor algebraically as well, so we'll go through a couple of different strategies. Our first strategy we should always try to apply is factor out a greatest common monomial first. So if we look at this first example, one of the first things to note is that each term is divisible by x. So I can factor an x out, leaving me with 6x squared plus 15x plus 6. But I'm not quite done yet, because each of these terms is still divisible by 3. So now we have 3x times 2x squared plus 5x plus 2. The reason I want to do this is because now I can apply some of the quadratic factoring methods that we've used in the past. So we can factor this by a table, or we can factor this by grouping, but ultimately 2x squared plus 5x plus 1 factors into 2x plus 1 and x plus 2. So it is important to note that these two, we could jump straight from the first to the third line if we recognize that 3x is the greatest common monomial. But that's why it's important to always check to make sure you've actually factored out the greatest term you can. So as we look at the second example, we've got 2x cubed minus 20x that we want to try to factor. First, it's important to note that each term is even and each term has an x. So I can factor out a 2x from the whole polynomial, giving me 2x multiplied by x squared minus 10. Now this is where this problem stops. The reason why we're not going to factor x squared minus 10 any further is because there's no two numbers that multiply to 10 that also add to make 0, at least not that are whole numbers. Right? We've seen something like this before, where if we had, like, for example, x squared minus 4, that could factor into x plus 2, x minus 2. Because 2 times 2 is 4, and 2 minus 2 is 0, so those terms cancel away. The reason this doesn't work for 10 is because the square root of 10 isn't a whole number, it's not an integer. But if we were allowed to factor over all the real numbers and not just the integers, we could factor it one further step. Square root of 10 is a little bit more than 3, and you can double check in your calculator. If you were to try to multiply this out, we will end up right back here. However, because we only factor over the real numbers, we won't take that step. Now this is a strategy we have talked about in the past. Always double check to make sure your polynomial is in simplest terms before you factor, because that'll make the rest of your factoring easier. And it might help you notice some of the special patterns. So there are 4 special patterns. A difference of squares is the difference of 2 squared terms, and it factors into a plus b, a minus b. So just so we can see an example, if we have something like x squared minus 16, that x squared is a perfect square term, so is 16, because the square root of 16 is 4. So this will factor into x plus 4, x minus 4. Similarly, if we have something like 25x squared minus 1, 25x squared is a perfect square because it's 5x times 5x. And 1 is a perfect square because it's 1 times 1. So this would factor into 5x plus 1, 5x minus 1. Perfect square trinomials we've seen in the past. We most recently used these when we were trying to complete the square. A perfect square trinomial looks like this, and it will factor to a plus b squared. So for example, we might have seen something like x squared plus 8x plus 16. That would factor to the square root of x is x. The square root of 16 is 4, so x plus 4 squared. Now, the 2 new ones, and I will prove that these are true in a future lesson. It's called the sum of 2 cubes and the difference of 2 cubes. Similar to our difference of squares, we have a cube term plus another cube term. Now, unfortunately, there's no easy trick for remembering how this factors. So if we have a cubed plus b cubed, it factors into a plus b, a squared minus ab plus b squared. The difference of two cubes rules is very similar, but if we have a cubed term minus another cubed term, it'll factor into a minus b, a squared plus ab plus b squared. The only difference between the two rules are these two signs, just trading places. Suppose, for example, we have 27x cubed plus 64. Now, 27x cubed is really 3x cubed. That is a cube number, and 64 is 4 cubed. So we have a sum of 2 cubes here. So we're just going to apply a rule where 3x is a and 4 is b. So I'll just write it in each step. So if 27x cubed plus 64 factors to 3x plus 4. 3x squared is 9x squared. 3x times 4 is minus 12x. And 4 squared is 16. If you don't trust me that these two polynomials are equal, pause the video now, multiply them out, and resume the video once you've convinced yourself it's true. But now let's take a look at a difference of two cubes as well. So let's say, for example, we have 8x cubed minus 27. So it's important to note that 8x cubed is a perfect cube. 8x cubed is really 2x to the third power. Similarly, 27 is 3 to the third power. So again, we have a difference of two cubes. I'll plug 2x in for A and 3 in for B. So it factors into 2x minus 3. 2x to the second power is 4x squared. 2x times 3 is 6x. And 3 squared is 9. So that is how 8x cubed minus 27 factors. So here's a fun fact about algebra. Any polynomial equation has exactly n answers where n is the degree of the polynomial. So this expression 8x cubed minus 27 has 3 roots. The question is, how many of them are real? How many of them are non-real? Well, I can say for certain that it has one real root at least. It has at least one real root because 8x cubed minus 27 equals 0 can be factored into what we just did, 2x minus 3, 4x squared plus 6x plus 9 equals 0. This tells me that it has a root, if we set that equal to 0, at 3 over 2. So that part of the equation has the other two roots, but I'll leave it to you to check to see if they are real or non-real. And finally, our last method is factoring by grouping, which we've already seen before. I showed you how to factor by grouping when we were factoring quadratic expressions. So our process to factor by grouping will pretty much be the same each and every time we have 4 terms in our polynomial. We'll group the first and second term together. We'll group the third and fourth term together. We'll look for a common factor, factor out, and then hopefully we can factor one more time. So let's take a look at these two examples. First, we've got x cubed minus x squared. I'll group those two together. And then x minus 1. In our first group, I can factor out an x squared, and that'll leave x minus 1 behind. In the second group, there's nothing really I can factor out, but I can always pretend to factor by taking out 1. Now, luckily, these both have an x minus 1 in common, so I can factor out the x minus 1, leaves me with x squared plus 1. Now, I'd like to point out, we might not necessarily be done. None of these should be taken in a vacuum, right? Always check to make sure nothing still factors. So always check to make sure there's no extra common factors. Always check to make sure you don't have any of your special patterns left over, which I think we'll see in this next one. So I'll group my first two terms, x to the fourth and x cubed. And x plus 1. So again, in the first group, I can factor out an x cubed. In the second group, it's the same as it was on the previous example. There's nothing I can really take out, but I can at least pretend to. So again, luckily, we have an x plus 1 in common. However, that x cubed plus 1, this is a sum of two cubes. Which means I'm going to have to factor that step one more time. So we'll leave the original x plus 1 alone off to the side for a second while we navigate this. So x cubed, well, again, that's x cubed. 1 is just 1 cubed. So I'm going to take my sum of two cubes pattern. I'll just copy and paste it. But for every a, I'm going to plug in x. For every b, I'll plug in 1. Which we can simplify. That's x plus 1, x squared minus x plus 1. And then here's that original x plus 1 I told you that we'd bring along for the ride. So this is the fully factored version of x to the fourth plus x cubed plus x plus 1. So that's it. That's 3 new tools for our toolbox for factoring polynomial expressions.